Okay, today's notes 1.8 should be mostly review from Algebra 2 or Algebra 3. We are adding a little piece to the compositions where we want to do domain, which you may or may not have done in Algebra 2. So there might be some new stuff, but overall it's mostly review, which is good because this is included on your quiz tomorrow, compositions. So you want to make sure you do your homework tonight, check your odds in the back, and make sure you're feeling comfortable with this. Title for today is combinations of functions. So basically we're taking two or more functions and putting them together somehow, okay, through mathematical operations. Those mathematical operations generally are the four operations you're probably most familiar with: add, subtract, multiply, divide. So I have up here the sum, difference, product, and quotient of functions, where f and g are two functions that have some overlapping domains. And what you're seeing on the left here, this is the way the book is going to notate it. So I just want to clarify what f plus g of x means. It really just means add the two functions, f of x plus g of x. So you can decide if you want to jot this stuff down. It's really mostly about notation, but you need to be able to read it the way the book is writing it so that you know, okay, I'm just adding the two functions or subtracting the two functions. The last one there, f divided by g of x. So we're dividing two functions. It's mainly just like put your function in the numerator, put your function in the denominator. But there does have to be a side note there that says g of x is not equal to 0. Why do we have to say g of x is not equal to 0? Because we're not allowed to divide by 0. The answer would be undefined. So we can divide the functions. That's allowed as long as g of x is not equal to 0. So that would be something that we would then exclude from our domain. So for our first set of examples, I'm going to give you two functions, an f of x and a g of x, and I'm going to have you do these four things. I want you to add, subtract, multiply, and divide. I think most of us are going to be okay just jumping right in, and we're just going to see if we can do this accurately. There are some operations where you have to be thoughtful about what you're doing, and we'll share out our answers and see if we agree with them in just a moment. So if you could at your desks, and you can talk to your group members if you need to, perform the operations. For f of x and g of x, where f of x is 5x squared plus 2, g of x is 3x minus 4. So can you add, subtract, multiply, and divide the two functions?
For adding. Oh, you think about 2 minus 4 plus 2 minus 4.
them together and see what we think. So right now on the board, all I really have is my setup for doing the function operations, adding, subtracting, multiplying, and dividing. And you may notice that I set up and I put parentheses around my functions. And you may be thinking, well, I don't really need those parentheses. That's true for some of them. So I put parentheses anytime I substitute in. So when I'm substituting in for f of x, I put it in parentheses. When I'm substituting in for g of x, I put it in parentheses in case I need the parentheses. So I'm doing it just in case. If I don't need the parentheses, then it's not a big deal. I wrote them and I move on. But if I do need the parentheses, then they're there. And this also happened on your summer packet quiz. You guys needed a set of parentheses, and not everybody had those set of parentheses. So in addition, the parentheses don't really matter. You don't need them to separate out the two functions because when you're adding functions, you're just combining like terms. I only have one set of like terms here. That would be 5x squared plus 3x, and then it will be minus 2. So I didn't really need the parentheses, but I had them if I needed them. Now, it does also ask you to list the domain of your new function. So when we look at 5x squared plus 3x minus 2, think about that function. It's quadratic. What's the domain of a quadratic function? All real numbers. So we could say that the domain of this, I can really put in any number that I want, would be negative infinity to infinity. Okay, so that's the domain of my new function. For f of x minus g of x, I still use my parentheses, and the first set of parentheses aren't that important, but the second set really are. So this happened, like I said, on your summer packet quiz. You were subtracting an f of x, and you want to subtract all of the function. In this case, I want to subtract all of g of x. G of x is 3x minus 4, so I want to subtract 3x, but I also want to subtract a negative 4, which means if I think about adding the opposite, this is going to be plus a negative and then a positive 4. Okay, so you have to be really careful when you're subtracting another function. You want to subtract all the different terms of that function, so they're all going to change signs, okay, not just the first one. Then combine your like terms, you get something like 5x squared minus 3x, and you should have plus 6. So double check to make sure that you got a plus 6 right there. Again, it's another quadratic, so the domain is all real numbers, okay? For f times g, a lot of times this is going to look like FOIL or distribution. Just multiply out all the terms and then combine like terms if you can. You should get 15x cubed minus 20x squared plus 6x and minus 8. Okay, we created a cubic function there. What's the domain for a cubic function? You can look at your 8 basic function sheet. All real numbers. You can cube any number you want. There's no rule about multiplying a number by itself X amount of times. So domain would again be all real numbers. All right, when we get to f divided by g, notice my setup is just to put function f in the numerator, function g in the denominator. Now, you can check for simplifying. If you're dividing things, you can basically simplify if you have common factors. So that would mean that these two functions would need to be in factored form. For 5x squared plus 2, there's nothing really to factor. They don't share any common factors. I can't factor that trinomial. It's factored. Okay? And same for 3x minus 4. It's a linear factor. There's really nothing for me to do right there. You cannot reduce the 2 and the 4, so check your work if you wrote 1 over 2. You are not able to reduce the 2 and the 4 because those are not factors. Those are terms in the functions. Terms are things that are being added and subtracted with other things. So 2 is being added with 5x squared. It's not a factor of that function. Okay? A factor would be something that was multiplied. Okay? So be really thoughtful there. Don't just cancel terms. Make sure you're canceling factors. So this is really as good as it gets. But now we have a rational function because we have a numerator and denominator. And we had said this will work as long as g of x is not equal to 0. What value of x makes g of x equal 0? 4/3. How'd you get that?
Just
Yeah, he's just thinking about, okay, I'm gonna subtract 4, so this has to be 4, right? And the only way for 3 times x to be 4 is if it's 4/3. If you're having trouble with that, you can also set it equal to 0, add 4, divide by 3, so x equals 4/3. There's your restriction. So that means in the domain, I'm just going to not include 4/3. Remember how we do that? Negative infinity to 4/3 with a parenthesis, so that's exclusive. Do not include 4/3 in union with 4/3 to infinity. So that's everything but 4/3. Right. So in that particular example, I used two polynomials, a quadratic and a linear, for f of x and g of x. And when I added, subtracted, and multiplied, I kept getting domains of all real numbers because I was just creating other polynomials. Besides rational functions, that's a function that looks like a fraction with a numerator and denominator. Do you guys know of any other functions that have restrictions to their domains? Radical functions if the root is even, right? So like a square root function, because what can't you take square roots of? Negative numbers. Okay, so there is always, if I were to give you like an f of x that was a square root function and ask you to do some of these compositions, then your domains may not be all real numbers because you have a square root in it. Does anybody know any other functions? That's the only one on your pink sheet besides the rational. There is one, yeah, that's the reciprocal is like the rational because it looks like a fraction, right? So denominator could not equal 0. There is one other one that you studied in Algebra 2, and it was the log function. So log is inverse of exponential, and instead of having a horizontal asymptote, it has a vertical asymptote. So there are some numbers you can't take the logs of. You can't take the log of 0, and you can't take the log of negative numbers. Side note. You probably won't have logs this chapter, so don't worry. All right, next up on the list of things to cover, compositions. Go ahead and jot this down so that you have it. There is a new notation in our pre-calculus textbook. You're probably more familiar with the notation on the right. Either one is acceptable. Note that the notation on the left does not say fog. It's just an open circle. Okay, so composition is something else that you can do with two or more functions besides just the basic operations, adding, subtracting, multiplying, and dividing. And essentially the thing that I always try to remember about composition is it's just substitution. Okay, so it's kind of like function notation in our warm-up. It's going to tell me what I should be putting in for x. And in this case, it's just telling me to put in another function for x. So it's like, instead of having x there, you're going to sub in another function, which will probably look like some other algebraic expression. So you can use either notation that you want to use. Just make sure that you're able to recognize the new notation here on the left in the textbook as it's asking me to do a composition, a substitution. Now, this note down here at the bottom, we're going to talk about when we do our example. The weird thing about compositions is when you do a composition, you get a brand new function. And the brand new function might look like it has a domain of all real numbers or a large domain. But you have to remember that your composition has an inside and an outside function. And when we think back to the warm-up, when we did f of 3, you do the inside function first. So you have to be able to do the inside function and get an output so that you can plug in the output into the composition or the outside function and get your final answer. So even though your final answer in your composition might look like it has a domain of all real numbers, because the inside function doesn't, then your domain of your composition is restricted. Okay, so you got to remember that this is not just a brand new function all by itself. I'm plugging one function in for x, so when I plug that function in, I have to be able to get an output. So you'll see when we do our first example what I'm talking about. Here's our first example. Let's let f of x equal x squared minus 4, and we'll let g of x equal square root of 4 minus x squared. We're going to find a composition, f of g of x, and then we're going to state its domain. Okay, again, I don't care if you use the old notation. I actually prefer the old notation because I spent more years teaching Algebra 2, so I'm used to that. And you can use either one that you want. We're going to take g of x, which is the square root of 4 minus x squared, and we're going to plug it in for the x in f. So when we write out f, we'll replace the x with g of x. So that would be square root of 4 minus x squared, that's my new x, squared, minus 4. You okay with my substitution? Anybody got any questions about why I did what I did? Okay, to simplify that, what happens? The square cancels the square root, so then we're left with 4 minus x squared minus 4, and then 4 minus 4 is 0. Okay, so our composition looks like negative x squared. Now, if I were being asked to state the domain, I might instantly think, oh, negative x squared, that's just a quadratic, domain is all real numbers. But I have to remember that when I do this domain for my composition, I first have to be able to plug into g and get an answer back out. So when you look at g and you notice that it's a radical or a square root function, do all numbers work in the square root function? No, they have to be positives or 0 in order for us to be able to get out an answer. Otherwise, they come out to imaginary answers. I heard you talk about imaginary numbers over there. So I want you real quickly with your group members to discuss what are the x's that work so that I can get positives or zeros underneath that radical. It's a little bit different than some of the other radicals we've looked at, so you got to think about it. What numbers work?
Yeah, the number is higher than the natural numbers.
Okay, what kinds of things work for x? 2 works. Okay, there is always some discussion about 2. When you do 4 minus 2 squared, that's 4 minus 4, which is 0. Can you do the square root of 0? Yeah, it's 0, so 2 works. Do things greater than 2 work? No, because then you're subtracting too much and you get a negative, and that doesn't work. Okay, so we know that the upper bound is 2 for this, okay, and it includes 2, so I'm going to use a bracket. What about the lower bound? Everything under 2 works? Alexander saying no. What doesn't work? Anything below -2, because when you square things, they're going to come out positive. So if I put in a -3 for x, that would be like -3 squared, which is 9, and then 4 minus 9 is -5, and I can't take the square root of that. So -2 is the last number that works. -2 squared gets us back to 4, which is then 0. So the domain for this will be -2 to 2. Remember, should be least to greatest in interval notation. So -2 to 2, inclusive, because the 2's work. And so that means, while I would normally say this domain would be all real numbers, because I have to be able to first plug into G and get an answer back out, I'm going to use the domain of G instead. So my domain for this composition is -2 to 2. We okay with that? All right, so I'm going to give you one more and let you work it out on your own. You can do the composition and then think about domain. Okay, and remember, when you're thinking about domain, think about the domain of the composition, but also consider the domain of G. Does that work? So here, f of x is the square root of x, and g of x is x minus 5. Do your composition and think about its domain. Oh, so in the composition, it's saying take g of x, which is the square root of 4x minus x squared, and plugging in 4x in f of x. So f of x starts with an x. This is replacing the x. Take it squared. Yes, the x minus 5. Okay, checking your answer on the board, f of g of x. You are to take g of x, which is x minus 5, and sub it in for x in the f of x function. So that would be the square root of x minus 5. There's nothing you can take the square root of there. So that's your new composition. And then you've got to think about domain. If you go back to g of x is a linear function, right? X minus 5. So its domain is all real numbers. A line continues on left and right in both directions. So I can put anything I want in for G and get answers out for G that I can plug into F. But when I look at my composition, I notice my composition is now a square root function. So I do have to consider the domain of my composition. What's the domain of my composition? Does everything work? No, what's the lowest number that works? 5. 5 minus 5 will be 0. That's the last square root I can do, square root of 0. So 5 is included, and then anything above 5 will produce positive numbers underneath the radical and should be included in the domain. So 2 positive infinity. Okay. So sometimes you're just looking at the domain of the composition and G is not affecting it. Other times the domain of the composition looks bigger than it really is. You have to go back to G and restrict according to that inside function. Any questions? All right, you've got some nice time here to go ahead and get started on that homework assignment. It's on your gold sheet.
Yeah, don't forget the book.